So this lesson's on higher order derivatives. We know that if we want the derivative with respect to x of y, that we can write that as dy dx. If we want the second derivative, if we want the derivative with respect to x of dy dx, what notation does that give us? We write it this way, because again, d dy, d2y, dx dx, dx squared, etc. If we want the third derivative, d dx of the second derivative, that would give us d cubed y, dx dx dx, dx cubed. So that's what the notation is. I'll just quickly do a couple of these. If I have f of x equals x squared, f prime of x is 2x, f double prime of x is 2, f triple prime of x is 0, f quadruple prime of x is 0, etc., all the way beyond. That's the f notation. The y notation would be y is x squared, dy dx is 2x, the next derivative, second derivative, d2y dx2 would be 2, the third derivative, d3y dx cubed would be 0, fourth derivative, d4y dx to the fourth, also 0. So that's the process we're working with. Now let's go ahead and look at the behavior of a trig function. So what do we know? We know if y equals sine x, the first derivative, dy dx, the derivative of sine x is cos x. The second derivative, d2y dx, would be the derivative of cos x, which is minus sine x. The third derivative, d3y dx cubed, would be the derivative of minus sine x. Pull the minus out in front, that is minus the derivative of sine x, which of course is minus cos x. If I want the fourth derivative, that would be the derivative of the third derivative, so the derivative of minus cos x. I can pull the minus out in front, so it's minus the derivative of cos x. So that's minus sine x, and we're back to where we started. So the fourth derivative of sine x is sine x, and that pattern will continue as we go. But let's look at some of our other functions. Let's take a look at tangent x. So starting with y equals tangent x. You can show using the quotient rule that the derivative of tangent is secant squared x, which would be sec x times sec x, maybe, if you want to think of it that way. How about the second derivative? What would that be? So d2y dx2 would be the derivative of secant squared x, which is the derivative of, if we're going to use the product rule, sec x times sec x. Well, to do that, let's call u sec x and let's call v sec x and go from there and see what we get. So we would say u equals sec x, v equals sec x, u prime, derivative of secant to secant tangent, sec x tan x, similarly v prime is sec x tan x. So if we're here then, what will we say? We would say d2y dx2 is u prime v plus uv prime. So u prime v, sec tangent times sec x tan x times sec x, that's u prime v plus uv prime, plus sec x times sec x tan x. So what does that become? What do we get? Well, distributing sec tan sec would be sec squared times tangent x. Plus, what do we have here? Sec x times sec x tan x would be sec squared times tangent x. So if we add those together, sec squared tangent plus sec squared tangent would be 2 times sec squared tangent. So that's one way for us to do it. Another way would be to use the power rule. Let's talk about the power rule. Let's remind ourselves of that process. Power rule. The derivative with respect to x of f of x to the n we pull the n down front, so it's n times f of x to the n minus 1 times the derivative of the inside times f prime of x, or times the derivative of f of x. So yes, looking at it with that other notation, another version of the power rule. N times f of x to the n minus 1 times the derivative with respect to x of f of x. So again, we wanted the second derivative. We started with y equals tangent x, and then dy dx is secant squared x, which of course means sec x to the second power. So using the power rule, the second derivative, d2y dx2, which is the derivative of sec x to the second power, pull the 2 down, 2 times the function sec x to the 2 minus 1 times the derivative of sec x. So what does this become? 2 times sec x to the first times the derivative of secant x, which is secant tangent. And you'll see we have the same answer we had before, which is 2 times sec squared x times tangent x. And let's do one more sort of in this vein to get a second derivative. If I want to get the second derivative of secant x, so let f of x equals secant x, find f double prime of x, just to be familiar with the other notation as well. So f of x is secant x. The first derivative is secant tangent. So the second derivative is the derivative of secant tangent. And to do that, we're going to play with the product rule. This time where u is secant and v is tangent. So u prime, the derivative of secant is secant tangent. And v prime, the derivative of tangent is secant squared x. So my f double prime of x will be u prime v plus uv prime. Which is going to be what? U prime v sec tan times tan plus uv prime plus sec squared. So we get sec tan, that's sec tan squared, sec x tan squared x plus sec squared to be sec cubed x. Now, there's nothing wrong with this answer. That would be the second derivative, but we might want to rewrite this. So remember one of our identities, which is that 1 plus tangent squared x equals secant squared x. So if that's the case, then tangent squared x is sec squared x minus 1. So I could replace this tangent squared with sec squared x minus 1 to see if it can look a little different. So where are we at currently? We are at f double prime of x is sec x tan squared x plus sec cubed x, and then we will replace the tangent squared with sec squared x minus 1. Second derivative is sec x times sec squared x minus 1 plus sec cubed x. So f double prime of x is sec times sec squared is sec cubed x minus sec x times 1 minus sec x plus sec cubed x. And you can see it has a different feel written this way. And we can say the second derivative is 2 sec cubed x minus sec x. And again, there's many, many other ways you could write it, but that's what we're seeing here. So let's go back to sine and cosine. And let's ask for the 9th derivative. So we're going to let y equal cos x. And I want the 9th derivative. So I want d9y dx to the 9th. So that's going to be a lot of work unless we can identify a pattern. And maybe you can. Y is cos x. His derivative, dy dx, is minus sine x. The second derivative, d2y dx2, would be the derivative of minus sine x. Which is minus the derivative of sine x, which is minus cos x. Third derivative is the derivative of minus cos x, which is minus the derivative of cos x, which is minus sine x, which equals sine x. So the fourth derivative is the derivative of sine x, and we're back to cos x. And you can see the pattern is going to continue. So continuing with this, then the fifth derivative would just jump to minus sine x. The sixth derivative would be minus cos x. The seventh derivative would be sine x. So the eighth derivative, again, we're back to cos x. And the ninth derivative, this is what we're looking for. The ninth derivative is the derivative of cos x, which is we're back to minus sine x. So you can see that this pattern repeats itself all the way around, going from cos to minus sine to minus cos to sine, cos minus sine minus cos minus sine, etc. So you can find any degree of derivative you need just by following that pattern.